Okay, hello everyone. Welcome back to the second class of CS224N. Okay, so right at the end of last time, I was just showing you a little from this Ipython notebook of things that you could do with word vectors, but I kind of ran out of time a little for a bit, so I'll just spend a couple of more minutes first showing the end of this. I stuck this Ipython notebook up on the course page, so under lecture 1 you can find a copy of it and you can download it. So I both stuck up just an HTML version of it and a zip file. Like the HTML file is only good to look at, you can't do anything with it, so you want to, if you want to play with it via yourself, download the zip file and get the Ipython notebook out of that. Okay, so we were looking at these glove word vectors, which I'll talk about a bit more today. And so there are these sort of basic results of similarity in this vector space worked very nicely for discovering similar words. And then going on from that, there was this idea that we'll spend some more time on today, which was maybe this vector space is not only a similarity space where close together things have similar meaning, but it actually captures meaning in a considerably deeper and more profound way, which is to say that there are actually directions in the space that you can point which have a certain meaning, so that if you're pointing in one direction, it means this is more so the case. If you're pointing in a different direction in the meaning space, it might be this is the capital of this country, or all sorts of different meanings could be encoded in the space. And a way of testing that is to use these analogy problems. And I quickly showed this at the end, but just to make sure everyone got it, since it's sort of a clever thing, right? So the idea is that we're going to start with a pair of words like king and man. And so what we're going to do is we're going to say, well, there's a vector for king in the space, and there's a vector for man in the space. But what we're going to do is we're going to subtract, as in just good old vector subtraction that you hopefully learned in your linear algebra class. We're going to subtract the man vector from the king vector. And the idea we have in our head then is if we do that, what will happen is we'll be left with the meaning of kingship without the manness. And so then there's also a vector for woman. So we could add the woman vector to that resulting vector. And then we could say, well, in the vector, we end up at some point in the vector space. And then we're going to say, well, what's the closest word that you can find to here? And it's going to print out the closest word. And as we saw last time, lo and behold, if you do that, you get the answer. I'm saying you get king, man, woman. No? Wait. I have to reverse king and... Oh, sure. Sorry. Whoops. Yeah. Okay, I can't even do it well live. Man, king... Oh, okay. Okay, yeah, that's right, sorry. Okay, yeah, because it should be man is to king as woman is to something. Sorry, yeah, I was getting my order of components wrong. Ooh, okay. And, you know, as I was I guess I was showing some examples last time with nationality words. But I mean, this, in a way that is sort of surprising to shocking, this actually works for all kinds of things that you can get meaning in this space. So I can ask various kinds of analogies of looser sorts. I can say Australia is to beer as France is to wine. You might think wine. What it gives back is champagne, which seems a pretty good answer. I'll go with that. You can do more syntactic facts, so I can say tallest to tallest as long is to longest, and it gets that. If I say good is to fantastic as bad is to terrible, that it seems to get out that there's some kind of notion of make more extreme direction and get this direction out. Oh, I skipped over one. Obama is to Clinton as Reagan is to... You may or may not like the answer it gives for this one, as Obama is to, as Reagan is to Nixon. Now, one thing you might notice at this point, and this is something I actually want to come back to at the end, well, there's this problem because Clinton's ambiguous, right? There's Bill and there's Hillary. I forget, you know, so this data, as I said, is a few years old. So this data was done in 2014. So it definitely doesn't have Trump really in it as a politician. But you know, it would have variously both Clintons. But it sort of makes sense of probably for sort of before 2014 data that Bill Clinton dominated. So I think what we're getting out of this is that Clinton and Nixon are sort of similar, of people in dangers of being impeached and on both sides of the aisle, and is thinking primarily of Bill Clinton. But this sort of brings up something that I'll come back to right at the end of, it sort of looks like we've got a sort of a problem here because we just have this string, literally Clinton, and that string is any possible sense and meaning of the string Clinton. And so minimally that we have Bill Clinton and Hillary Clinton, but you know, maybe you have some friends that are called Clinton as well, right? And they're all mixed together in this Clinton. And so that seems kind of problematic. And that's sort of been an issue that's been discussed some for these word vectors, and I'll come back to that. Another thing you can do is you can give a set of words and say which is the odd one out. Maybe you used to do puzzles like that in middle school or something. And so you can do that, and it decides that cereal is the odd one out of that set. Yeah, seems okay. And then one other thing I'll just show you is, so it'd sort of be nice to look at these words as I've drawn them in some of the slide pictures. So this is saying to put together a PCA, principal components analysis scatter plot. So I can do that, and then I can say, give it a set of words and draw me these as a scatter plot. And hopefully, if I can just about fit it in, here is my scatter plot. And it works pretty well, right? I've got the wine, champagne, beer up here, then the coffee and tea. Here are the countries. Here's the schools, college, institute, universities. The animals are down here. Foodstuffs there. So yeah, this sort of really does work with this two-dimensional display. It basically shows you similarity. Now, there are, you know, to some extent, though, you want to hold on to your wallet with these PCA displays, because as I've discussed before, since you were taking something that was 100-dimensional and we're just doing this 2D projection, that is capturing some of the major geometry of the space, but it just has to be losing a huge amount of the information. So when things end up close together, they might be really close together in the original space, or they might just have been words that lost in the 2D projection because there are other patterns that were more dominant and were chosen as the first two principal components. So you sort of don't want to over-trust these things, and something, if you like InfoVis, you might think about is how there are other ways that I might be able to represent the distances in a way that was more accurate. But anyway, this is very simple to do, right? I'm just getting a PCA to reduce the dimensionality of the matrix and then transforming with it these word vectors and printing them. It's mainly easy to do. The bit that wasn't easy for me to do, but if someone's got some clever Python plotting tips, I'd like one if someone wants to send me a message after class. I would have thought there'd be some default way in which you could just label points in a scatter plot, but I wasn't able to find one. So what I did was I'm just sort of plotting the text and I'm offsetting it a little bit from the points. Now that works kind of crappily because they just collide with each other, as you can see. So it would be better if there was a better way to do point labeling in Python plots. So if anyone knows the answer to that one, you can send it to me. Okay, so that's that. And if you haven't used the Ipython notebooks before and you don't want your computer to run really slowly, it's a good idea to halt your Ipython notebooks when you're not going to be using them anymore, especially if they're computing something. Okay. Okay, so now lecture 2. So for today, we're going to keep on talking about things you can do with word vectors and say a little bit at the end about word sensors. So in more detail, I'm going to say a bit more about word to vec. I'm going to have a sort of a very brief excursion on optimization. But then I sort of want to explain a bit more of the space of what people have done and can do with dense word representations. So I'm going to say something about count-based approaches to capturing meaning and how do they work. I'm going to talk for a bit about a different model of word vectors, which was the glove model that a postdoc of mine, Jeffrey Pennington, and me worked on a couple of years ago. Talk some about evaluation, really a quite dominant theme on a lot of what we do in natural language processing is how do we evaluate things and how much do we trust our evaluations, and then say a little bit about word sensors. I have a sort of a goal here, which is that by the end of the class, you should actually sort of understand enough of the lay of the land that you could read papers about word vectors, such as the ones that are in the syllabus, and actually understand them and where they're coming from and roughly how they work. And so, you know, if you really want to minimize work for this class, you could think, oh, I know everything I need to know after the first week, and I'm going to do a final project on word vectors, and I'll be okay. And, you know, you could actually do that. I'll mention during the class a couple of recent pieces of work on word vectors. On the other hand, doing things with word vectors is a fairly mined out area, so you're probably better off also listening to some of the later parts of the class. Okay, so remember we had this idea of word to vec, so it was an iterative updating algorithm that learned these vector representations of words that in some sense capture their meaning. And the way it worked was we kind of moved position by position through a corpus, and each point in time we had a center word here into, and it's trying to predict the words around it by having a probability distribution over words that will occur around it. And that probability distribution is defined simply in terms of the dot product of the word vectors via the softmax function. And so what we want to do is change those vectors in a way that this gives good probability predictions. It gives as high probability as possible to words that you tend to see in the context. And so just to drill that in a little bit more, you know, what we actually have is we have two matrices, right? We have, for center words, we have a matrix where for each word in our vocabulary, we have a vector. And this is probably as good a point as any to say that it turns out that all the major deep learning packages, TensorFlow, PyTorch, etc., for their word vectors, the word vectors are represented as rows. If you've done a bunch of math classes, that might not be what you would expect. You might have expected the other way around, but they all put them in rows. So we can have rows for our, so we have 6 words and a 5-dimensional vector each. Okay, and then we have this outside matrix where we also have a second vector for each word, which is this representation in context. So when we have a particular center word here, word 4, you know, when we're doing our computations, we're taking a dot product between v4 and each row of u, and that's then giving us a vector of dot product scores. And so then after that, we're running softmaxes on each of those numbers, doing it element-wise, and that's then giving us a probability distribution over words in the context. And there's sort of things to notice there, which hopefully you noticed last time, but to make sure you noticed it, you know, we've just got one probability distribution, right? So in terms of what words we predict, we're predicting exactly the same probability distribution every position. We're sort of saying the most likely word 1 to the left is whatever it is, house. The most likely word 2 to the left is house. 3 to the left is house. The one to the right should be house 2, right? So it's sort of no sort of fineness of prediction. It's just an overall kind of probability distribution of words that are likely to occur in my context. So all we're asking for is a model that gives reasonably high probability estimates to all words that occur in the context of this word relatively often. There's nothing more to it than that. And that's part of why it's sort of surprising when you've got such a simplistic thing that it seems like at the end of the day, it can end up capturing so much about the meanings of words and aspects of the meanings of words, like in the examples I was just showing you in the Ipython notebook. And there's one other thing I was going to say. Oh yeah, the one other thing I was going to say was the other thing that might occur to you from this is, well, wait a minute, there are words like the and of that occur all the time. So that means every word must have a high dot product with words like the and of and to get their probabilities right. And the first answer to that is, yep, that's true. And it turns out that all word vectors have a very strong word probability component that reflects that. And I mean, one of the things that some work has discussed, so on the readings, there are 2 papers from Sanjeev Arora's group in Princeton, and one of those papers sort of discusses this probability high frequency effect. And a crude way of actually fixing this high frequency effect is that normally the first biggest component in your word vectors is actually a frequency effect, and if you just lop it off, you can make your semantic similarities better. But there are other things that we do to sort of deal with high frequencies. Okay, so we get these lovely spaces that I've shown some of. But I'll make one more remark. Yeah, so did I say this last time? Uh-oh. My remark anyway is that we show all these 2-dimensional pictures. They're exceedingly misleading because in these 2-dimensional pictures, you have these effects that if, Samsung is close to Nokia, it has to be over here, and then it has to be far away from words that are over here. Whereas you might sort of also want to have the effect that Nokia is close to Finland for a different reason. And you can't do that in 2-dimensional vector spaces. But one of the most of the properties of high-dimensional vector spaces are very unintuitive, and one of the ways that they're unintuitive is in a high-dimensional vector space, a word can be close to lots of other words in different directions. Okay, so we sort of started to talk about how we went about learning these word vectors. I'm sort of going to take about a 5-minute detour into optimization. Now, this isn't really an optimization class. If you want to learn a lot about optimization, well, you can learn more about optimization if you do 229, and if you do something like Stephen Boyd's optimization class, you can learn a lot of optimization. But this is sort of really baby optimization, but just to make sure everyone's on the same page, here are 3 slides, right? So what we did at the end, what we did over there, where I apologize that my writing was too small, but that will give you the chance to, when doing homework too, and you have to write that out, to work it out for yourselves and learn more in the process. Right, so what we had was a cost function that we wanted to minimize, and so what we did was we did our bit of calculus to calculate the gradient of the cost function with respect to our word vectors, which were our variables theta. And then what we want to do is say, well, if we take a small step in the direction of the negative of the gradient, that will be taking us downhill in this space. And we want to keep on doing that and sort of head to the minimum of our space. I mean, of course, in our high multidimensional space, you know, it might not be a nice smooth curve like this. It might be a horrible and non-convex curve, but that's just the idea. So essentially, we're saying we've got the old parameters. We work out the gradient of the objective function using those old parameters. We multiply that by a small alpha, which is our step size or learning rate, because we only want to move a little bit each time, because if back here, if we sort of said downhill is this way and said, great, let's go a long way that way, you could kind of completely overshoot. So we only want to go a little bit each time. So we normally have a small learning rate alpha, and so we subtract a small multiple of the gradient and from the old parameters, and we get our new parameters. And that's sort of effectively being worked out component-wise, as is shown below, that we're just doing that for each of the partial derivatives. And then that our hope is that that will let us gradually walk down this surface. Now, if you actually did this, it would be unbelievably bad for the kind of systems that we built. And there's a lot of work on clever optimization, but the most basic thing, which you definitely need to know, is that, well, our objective function here, j of theta, was a function of our entire corpus, right? And to get this to work well, the first thing you want to do is, you know, collect a few billion words of your favorite language and then say, go and build a word-to-vec model for me. And so if you have to evaluate a billion center words and maybe then for each of 10 billion context words, if you have a window size of 5. And so you have to do these sort of 10 billion softmax calculations before you work out what your gradient is, that you're going to be having your computer compute for quite a long time before you make one little step in the gradient. And so things are going to go so slowly. So no one does that in deep learning systems. So what everyone does is use stochastic gradient descent. And in stochastic gradient descent, we sample a window in the simplest case. We, just for this one window, work out an estimate of the gradient, and we use it as a parameter update. So this is sort of an amazingly noisy estimate of the gradient, but it sort of doesn't matter too much, because as soon as we've done it, we're going to choose a different center word and do it again and again, so that gradually we sort of approach what we would have gotten if we'd sort of looked at all of the center words before we took any steps. But because we take steps as we go, we get to the minimum of the function orders of magnitude more quickly. So this shows the simplest case where we're just sampling one window. In practice, that's not what we normally do. We normally sample a small bunch, you know, order approximately 32 or 64. So if we have a sample that's bigger, that's generally referred to as a mini batch, and we calculate a gradient estimate from the mini batch. So that has two advantages. One advantage is that you kind of get less noisy estimates of the gradient because you've kind of averaged over a bunch of examples rather than just using one. But the second advantage, which is the one why we really care, is if we want our computations to go fast when we're using a GPU, that you need to get parallelization of doing the same operation a whole bunch of times, and then you gain a lot by using a mini batch of 64 examples or something like that. And you don't have to, but you know, it turns out in the details of the guts of the hardware that, you know, these NVIDIA GPUs, you know, have these whatever they have inside them that are in powers of 2. So you get better speed ups if you use batches like 32 or 64 rather than just deciding that 42 is still your favorite number from high school and you're going to use that as the size of your mini batch. Okay. Yeah, here's one other interesting thing which actually has some optimization details in it, it turns out. If you think of these doing stochastic gradients with word vectors, that's actually very different to some other deep learning problems like vision deep learning problems, because for either a single window or even a sort of a reasonably sized mini batch, it'll turn out that that mini batch only has you know, relatively speaking, a handful of words in it, right? So if you have a mini batch of size 32 and a window size of 10, you know, probably there are only about 100, 150 different words in it, but yet we're building this model over a vocabulary of 250,000 words or something like that. So just about all of the elements in this vector are 0. And so we sort of really have this very sparse parameter update. And so that sort of suggests that we actually probably want to sort of only update the word vectors that appear. And then the question is whether you can achieve that, right? The dumb way to do it is you just have this matrix that's normally nearly all zeros, and you say, add those two matrices together, and there you go. And then the question is, can you actually have a sparse matrix update which only updates the certain rows of the matrix that contain the words that you've entered and do things much faster? And if you're doing something even cleverer, like doing distributed computation over multiple computers and sharing your parameters, well, then definitely you sort of only want to update the word vectors that you've actually been getting a parameter estimate for. So there's sort of some details there, but I'm going to skip past them. More details. Right, so a couple of people asked afterwards, yeah, why are there these two word vectors, the sort of center and the outside one? And I mean, the answer to that is it makes that math I showed you easy, right? So that if you do it as I showed you, well, you know, for working out the partial derivatives for the center word, it's just as I showed you, it's easy. But if you use only one set of word vectors, well then the same word that's the center word will be one of the choices for the context word when you're working out that softmax for the context word, and then you'll get these terms that are then squared terms in terms of the two references to that same word, and that makes your math more difficult. So it's sort of just a practical thing in the end. I mean, it sort of doesn't make very much difference, because if you sort of think about it, since you're going along through all the positions, you know, what was a center word at one point is immediately afterwards a context word of what used to be a context word, which is now the center word. So you're sort of doing the same computations because, you know, the dot product is symmetric actually. All over again. So they get pretty similar vector representations. So it seems like in general you can get the best results by averaging what comes out for your two vectors, and you end up with just one vector per word. Okay, more substantively, if you go to the word2vec paper, you will discover that there's sort of more to word2vec, that they define as sort of a family of word2vec models. And there are sort of two main parts of that family. Firstly, there's a choice between the continuous bag of words model and the skipgrams model. And what I presented was the skipgrams model. So in the skipgrams model, you've got one center word, and you're trying to predict all the words in context one at a time. For the continuous bag of words model, it's the opposite. You've got all of the outside words, and you're trying to use all of them, though considered independently like a naive Bayes model, to predict the center word. And then the second one is the way I presented learning this was the method that's using the so-called naive softmax. So that for when we were wanting to work things out, we were sort of saying, okay, we want probability estimates for the context words, and so we're just going to sum over the whole vocabulary, and we'll come up with these probability estimates. In practice, that turns out to be a sort of a bad idea, because that would also make things mega slow. So in homework 2, coming up next week, you will get to implement a much more practical way of doing this, which they present in the word2vec papers, right? So the problem is, if we're using this equation that we use to do the calculus, that down in this denominator here, we're doing the sum over the entire vocabulary. So if you have a vocabulary of 250,000 words, we're sort of doing 250,000 dot products and exponentials and adding them all to work out that denominator. And that sort of seems sort of a really bad idea if you want things to be fast. Thomas Mikolov and colleagues came up with this idea of negative sampling would be near enough. And so the idea of negative sampling is we're going to train binary logistic regressions instead. And so we're going to train one binary logistic regression for the actual word observed, what's in the numerator, and you want to give high probability to the word that was actually observed. And then what we're going to do is we're going to sort of randomly sample a bunch of other words, they're the negative samples, and say they weren't the ones that were actually seen. So you should be trying to give them as low a probability as possible. Okay, so the sort of notation that they use in the paper is sort of slightly different to the one I've used. They actually do maximization, not minimization, and that's their equation, which I'll come back to. But before we do that, here's the sigmoid function. So the sigmoid function is normally written like this, 1 over 1 plus e to the minus x. But essentially, the sigmoid function is like a binary case of the softmax function, right? That we have two possible outcomes, yes and no, and that you're sort of, again, got an input that is any real number, and it's mapping it onto a probability distribution between 0 and 1, which represents these two binary outcomes. And to the extent that the number's positive, it kind of ceilings to 1, and negative goes down to 0. Okay, so at this time, we're going to take the for the good word, we're going to take the dot product of the two vectors, shove it through a sigmoid function, and then we're going to want that probability estimate to be as high as possible. So if I show you this version, which is just written slightly differently to look as much as possible like the notation that we used last time, here is our new objective function for using negative sampling. And we've got two terms. The first one is the log of the sigmoid of the observed context word, the outside words, dot producted with the center word. And we're going to want that to be big. And then on the other hand, we've got the randomly chosen k-words, which are just other words, and we're going to work out dot products between them and the center word, and we're going to want those to be as small as possible. Note that extra minus sign in there, which is causing the sign of the two things to be different. Right, so those are our negative samples. And for big K, it can be a reasonably modest number. You can just take kind of 10, 15 negative samples, and that works pretty fine. I said we sort of sampled some words to be the negative samples. They in particular propose a sampling distribution that helps them along a little in partly dealing with this problem of very frequent words. So the starting point of how you sample words is you use what we call their Unigram distribution. So that just means you take words in a large corpus and count up how often each one occurs just as a count of independent words. So those are called unigram counts. And so you start off with unigram counts, but then you raise them to the 3/4 power. And raising to the 3/4 power has the effect of decreasing how often you sample very common words and increasing how often you sample rarer words. Okay, and that's that. Okay, so that's everything about word to vec I'm going to say. Anyone have any lasting? Yes? This is, sorry, Z, that capital Z is often used as a normalization term. And so this is saying, well, if you want, the probability distribution of words is you work out this 3/4 power of the count of the word for every word in the vocabulary. And then these numbers, you just sum them up over the vocabulary and it'll be sum total. And we're dividing by that, so we get a probability distribution. good question, because I hadn't explained that. In this class, when you see the letter Z with no explanation, it normally means I am a normalization term to turn things into probabilities, and you sort of iterate over the numerator term and summing them and divide through. Any other questions of things I haven't explained or otherwise? Yes?
So the window length, that's a pre-specified hyperparameter.
Yeah.
Right?
Yes, so what size window do you use? I'll actually come back to that in a bit and show a little bit of data on that. But yeah, we haven't done anything about that. At the moment, we're guessing a window size like 5, which isn't a bad one. But you know, there hasn't really been any science behind that, that people treat that as what's then called a hyperparameter, which means that you try a few different numbers and see which one seems best, and that's the one that you use in your future work. Yeah?
Was the 3/4 power chosen for any theoretical reason, or just because it seems to work in practice?
No. That was also chosen as a hyperparameter that improved performance. I mean, actually, you know, for this Word2Vec paper, I mean, you know, it turns out that in the actual paper, the model looks fairly clean, but what people discovered when they started digging through the code, which to their credit they did make available, reproducible research, that there are actually a whole bunch of tricks of different things like these hyperparameters of how you sample and how you weight windows and various things to make the numbers better. So, you know, people play quite a few tricks to make the numbers go up, which aren't particularly theoretical. Are we good? Yeah.
Speaking of which, I know a lot of like TensorFlow where like there's a lot of backends that that like default towards instead of sampling and getting back in time random, you just take the entire set and then divide it up and just kind of go through different sections. So is there a big difference, or is there like a difference you've seen in the back of this group?
Sometimes. So in general, for a lot of these sampling things, it's a bad idea if you're going to be doing multiple passes. If you just go boom, 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 and then boom, boom, boom again, that's a bad idea. But a common technique a lot of the packages use is that they do use a shuffling operation at the beginning. So for each epoch, they'll shuffle the data randomly, and then they'll go through it in sequence. And that has the benefits of faster computation from locality, etc., while meaning that when you do a different epoch, it will work out differently. Yeah. Yeah.
On that last question, is that comparing MapReduce or mini-batch to stochastic gradient descent?
Right, that last question I think was talking about taking the mini batches from the corpus and contrasting whether you actually say sample 20 randomly from the whole corpus versus just sort of working from left to right. Do you have a question?
Yeah, sitting in like the
yeah, so you could argue whether or not this was written in the clearest way, but right, so we're making this dot product and then we're negating it, which is then flipping which side of the space we're on, right? Because the sigmoid is symmetric around 0. So if we've got some dot product and then we negate it, we're sort of working out a 1 minus probability. And so that's the way in which we're actually, for the first term, we're wanting the probability to be high, and then for the negative samples, we're wanting their probability to be low. Okay, I'll maybe run ahead now. So this was an algorithm which sort of, you're going through this corpus position by position, and you're sort of doing this prediction of words, and then you're updating some parameters and you're learning something. And, you know, by Jove, it seemed to work based on what we saw in the examples. But, you know, you might have thought that was kind of weird, right? Look, we have this whole big pile of data, you know, sort of traditional thinking of statistics, right, is if you have a big pile of data, you aggregate it, and it sort of seems like there are obvious things you could do here. You could say, well, there's a word like whatever word we're using, banana. Let's just see what words occur in the context of a banana and count them all up, and then we'll be able to use those to predict somehow. And you know, those kinds of methods were traditionally used, including even with distributed representation techniques. So I want to say a bit about that so you're fully educated and don't sound like one of those people who are aware of no work that happened before 2013 when neural networks took off. Okay, so what we could do is we can essentially do the same thing as sort of word2vec. We could say there's a 5-word window around each word instance. That's often referred to as a word token, right? So in NLP, we often want to distinguish between a particular kind of type like banana or apple versus particular instances of it in the text, and that's referred to as sort of a type token distinction. So we could look at each token of a word and the words 5 around it, and then we could sort of start counting up which words occur with it. And so we can then have a matrix of co-occurrence counts. Okay, so we'll have again, and I'm going to give an example of this. So normally, again, you use a 5 to 10, but you know, I can just use a window of 1 to keep my counts very simple and small. I ignore left or right, just like word2vec did. And so if I have a teeny baby corpus like this, you know, what I could do is just say, here's a matrix of word co-occurrence counts. So within my window size of 1, I occurs next to like twice. And that means that like occurs next to I twice, it's symmetric, and all my other counts here are singletons. And so this gives me a big, huge, sparse matrix of word co-occurrence accounts. And so one thing that you could do is just use this matrix directly, because I haven't really got enough data here, but you know, if you sort of decided that, you know, the word like is like the word learning, what you'd do is you'd expect that these two vectors would end up kind of similar to each other. And you know, they do. So you could just measure similarity of the vectors directly in terms of these co-occurrence counts. But you know, it's a little bit unappealing doing things this way, right? If you have a 250,000 word vocabulary, that's where you're in this space where my math is bad, but it's in the trillions of the number of cells of this matrix. Might require a lot of storage, though if you're clever and notice that most of the cells were 0 and could do some clever sparse matrix representation, it might take a little bit less. Your classification models might have sparsity issues because, you know, a lot of those cells aren't present and so might not be very robust. And so there was a traditional answer to all of these things, which is, well, maybe we could have that big co-occurrence count matrix and somehow reduce its dimensionality of just find a corresponding low-dimensional matrix which preserves most of the information in the original matrix, and you know, maybe it'll reduce things to a dimensionality of somewhere around the size 25 to 1,000, as is done with word2vec. So there's sort of a standard, most common way of doing this dimensionality reduction, and you don't really have to understand all the math, but you get to play with this in homework 1, which is for any matrix, you can do what's called the singular value decomposition, which is a way you can take an arbitrary matrix and decompose it into 3 matrices, where the center one is diagonal and has what are called singular vectors, which are weightings of the different dimensions. So they decrease in size as you go downwards. And then these 2 U and V are then orthogonal bases corresponding to the rows and columns. And so in particular, it's even simpler in the case where we just have these word-word vectors because you have a square matrix, and so they're effectively the same. But you know, for the general case, although you get these sort of full orthogonal bases, you then have these bits sort of don't really matter because they end up being used for nothing when you work out the product. And then if you want to reduce the dimensionality, what you say is throw away the smallest singular values, which remember they're in decreasing size. And that means you're then effectively throwing away rows and columns of these other matrices. And then it says, behold, I've now reduced these things to a two-dimensional representation from the original three-dimensional representation. And that's referred to as the reduced SVD. And the classic result is in terms of least squares error in estimation, that the product of these three things will give xk, which is the best rank k approximation to the original x in terms of a x squared, least squares criterion. So we could do this and we could build word vectors. So I can make use of NumPy's SVD function, and I can throw into it matrices, and I can make word vectors, and these ones look really bad, but hey, I give it a data set of 3 sentences, so this isn't exactly a fair comparison. But so this technique was popularized around the turn of the millennium. It generally went for sort of word applications under the name of latent semantic analysis or latent semantic indexing, and the idea was that you could have these semantic directions that you were finding in this low-dimensional space that had meaning. And people worked with it quite a bit for techniques like trying to do information retrieval using these LSA approximations. And it sort of worked a bit. It kind of never really worked very well, I think. And so it never sort of hugely caught on. But it's sort of, the methods kind of continued to be explored, actually, mainly in the sort of cog-sci community where people were doing things with word meaning. And there's this sort of kind of interesting lacunae to the literature that there was this guy, Doug Rohde, who did a PhD at CMU in 2005. And basically what he discovered was, look, if rather than just using raw counts, I start doing quite a bit more in terms of, you know, fiddling with the counts, I can start to produce results that are much better. So rather than using raw counts, you have to do something to deal with those very high frequency words. So one idea is you could log scale them, which is also commonly used in information retrieval. Another idea is you could just use something like a ceiling function. So you take the minimum of x comma t for t set to some number like around 100. He used the idea, which was also another of the hacks that was put into the Word2Vec, was rather than just treating the whole window the same, that you should count words that are closer more. So in Word2Vec, they sample closer words more commonly than further away words. In his system, you're sort of having to have a differential count for closer words, etc. And then compared to any of that, rather than using counts at all, he then started using Pearson correlations, which helped, except they're sometimes negative, and he decided that it helped if you then got rid of the negative values. So in some sense, this sounds like a bag of hacks, but on the other hand, he was able to show that, you know, these transformed counts could actually then give you very useful word vectors, as I'm about to show. And, well, we have to realize that actually in slightly different forms, several of these exact same counts are actually being used in Word2Vec as well. Do you have a...
Yeah, were they evaluated the same way, like Word2Vec?
Yeah. So that's an... I'm about to show exactly that. That's actually a really interesting little bit of the data. So, you know, yeah, so the thing, if you do that, you not only get word similarities that are pretty good. Let me show you this example, which is cleaner. So the precise idea of evaluating with analogies was not something that had really been developed. So that was actually something that Tomasz Mikolov suggested. But actually, Doug Rohde made this really interesting observation, which was, he said, look, once I do these kind of transformations to improve the semantic representation of my word vectors, look, this really interesting property emerges, that what you find is that there are semantic vectors which are basically linear components in my carefully constructed space. So here we have the sort of verb to the doer of the verb direction. Drive, driver, clean, janitor, swim, swimmer, learn, teacher, or teach, teacher, doctor, treat, priest, pray. I mean, you know, it's not exactly perfect. You know, there's a little bit of wiggle there, right? But, you know, roughly, it's completely clear that there's sort of a direction in the space that corresponds to from a verb to the doer of a verb. And yeah, so he hadn't discussed, no one had thought of this idea of doing the analogies tests, but the thing in retrospect that's obvious is if you can construct a vector space that has this linearity property, then you're definitely going to do well in analogies. So effectively, he had invented a vector space that would do well in analogies, because this means that you've got this direction, which is the doer, and then you can immediately say that's the doer vector, which you can get from subtracting clean from swimmer, and clean from janitor, and then we can add it onto swim, and we'll get somewhere close to swimmer. So his space actually did do that. And so the moral in some sense is if you kind of do carefully controlled accounts and so on, that conventional methods can also give you good word vector spaces. And I mean, so that was actually the starting off point for our work on GloVe. So that essentially there'd been these two schools of work. There'd been this school of work that had been explored more in cog-sci than anywhere else, which had been based on counting and transforming counts. And, you know, it had some advantages, or it seemed it had some advantages, right? That you're making sort of efficient use of statistics because you're using the global statistics of the whole matrix directly to estimate things. And at that point, up until then, it had really only been used to capture word similarity, and a lot of it had suffered from disproportionate importance given to large counts. But Doug Rohde had sort of started to show how to solve both of these problems. And so on the other hand, there'd been these neural network methods, which are kind of direct prediction methods that we were defining that probability distribution and trying to predict the words that occur. And they had some advantages, right? The fact that you're sampling means that you're not going to run out of memory, hopefully. I know we've had some memory problems with homework 1, but in principle, you're not in as bad a memory position than if you have to construct a huge matrix because you're going linearly. But, you know, since you're doing it sample by sample, it's inefficient use of statistics. Okay, and so, but on the other hand, Mikolov's work, it performed perfectly. Oh, not perfectly, but really well. So this sort of led into this work that Jeffrey Pennington, Richard Socher and me did of, can we sort of combine these ideas and sort of have some of the goodness of the neural net methods while trying to do things with some kind of count matrix. And so in particular, we wanted to get the result in a slightly less hacky way, that you want to have components of meaning being linear operations in the vector space, that they're just some vector you're adding or something like this. And so the crucial observation of this model was that we could use ratios of co-occurrence probabilities to encode meaning components. And so the idea here is if you have a word like ice, and you say how often the thing's going to co-occur with it, well, solid should co-occur a lot and gas shouldn't. But, well, water's also going to co-occur a lot and some random word won't occur much. If you have, steam, you get the opposite pattern with solid and gas, right? But, so the thing to notice is it's not enough to just have large by itself, because large appears both here and here, or small appears there and there. The thing that's interesting is sort of the difference between these components, and they're indicating a meaning component. And so we can get at that if we look at the ratio of co-occurrence probabilities. And so for the ratio of co-occurrence probabilities, this is a dimension of meaning, and where for other words, this sort of ratio cancels out to about 1. And so in this slide, I've moved so it's not my small and large, but these are actually actual counts from a corpus. So we roughly get dimension of meaning between solid and gas, other ones coming out as about 1 because they're not the dimension of meaning. And so it seems like what we want is we want to have ratio of co-occurrence probabilities become linear in our space, and then we're in a good business. And so that's what we want to set about doing. Well, how can you do that? Well, the way you can do that is by, if you can make the dot products equal to the log of the co-occurrence probability, then immediately you get the fact that when you have a vector difference, it turns into a ratio of the co-occurrence probabilities. And so essentially the whole of the model is that we want to have dot products or logs of co-occurrence probabilities. And so that's what we do. So here is our objective function here, and it's made to look a little bit more complicated, but essentially we've got the squared loss here, and then we're wanting to say the dot product should be as similar as possible to the log of the co-occurrence probability, and so there'll be loss to the extent that they're not the same. But we kind of complexify it a little by putting in bias terms for both of the two words, because maybe the word is just overall common and likes to co-occur things, or uncommon or doesn't. And then we do one more little trick, because everyone does tricks to make the performance better, is that we also use this f function in front so that we're sort of capping the effect that very common word pairs can have on the performance of the system. Okay, and so that gave us the glove model of word vectors. And theoretically, the interest of this was, you know, a lot of the preceding literature there'd been these count methods and there'd been these prediction methods. And the hope was that this could sort of unify the two by showing you how you could have a method that is estimated simply off a count matrix, but it's done in the same kind of iterative loss-based estimation method that's used for the neural methods to get good word vectors. And this also worked to give good word vectors. So here's glove results for the word frog. And frogs and toad are obvious, but you know, these different kinds of words, various kinds of pretty tree frogs and things like that. Okay, so I'll then go from here and say a little bit more about some of the work on evaluating word vectors. And this is maybe also a chance to just talk a little bit about evaluation altogether. So normally in NLP, when we do evaluation, the first thing that comes up is intrinsic versus extrinsic evaluation. So normally if there's something we're trying to do, like model word similarity with word vectors, or we're trying to put parts of speech on words or something, we can just have an intrinsic evaluation of saying, how good a job did you get? Are you guessing the right part of speech? Are you putting synonyms close together? And that's sort of normally very easy to do and fast to compute. And it's useful to do because it helps us understand the system. On the other hand, a lot of the time those intrinsic evaluations, it's not very clear whether having done well on that task is really going to help us build the amazing natural language understanding robots that we so ardently desire. So people are also very interested in extrinsic evaluations. And so extrinsically is then saying, well, suppose you use this new stuff in a real system, does it make performance go up? and it's then sort of definitional what counts to you as a real system, but normally that's meaning it's some application that human beings actually care about and like to use. So that's something like web search or question answering or a phone dialogue system or something like that, that you can put it into that system and the numbers go up. So that seems what you want to do. You want to have stuff that works in real tasks. Of course, there are sort of, on the other hand, a lot of things are a lot harder then. So it's much more work to do such an evaluation and to run different variants of a system. And even when the results are poor or great, sometimes it's hard to diagnose. You know, if your great new word vectors don't work better in the system, you know, it might be for sort of some extraneous reason about how the system was built. It's sort of hiding all your magic. And if you just change the rest of the system, it would suddenly show its good effects. So it's kind of hard to do sort of apportionment of goodness and badness. Okay, so today I'm mainly going to say a little bit more about these intrinsic word vector evaluations that we've talked about. So we've talked quite a bit about these analogies. So if we're actually working out the analogies, it turns out that normally what people are doing is working out a cosine distance, an angle between different word candidates, to work out which is the word that solves the analogy, which is another little tiny wrinkle of difference there. And there's also one other trick that people commonly use. They forbid the system from returning one of the three words you put into the analogy. Okay, but nevertheless, so this is something that you can evaluate. Here are now some glove visualizations, and so these glove visualizations show exactly the same kind of linearity property that Doug Rohde had discovered, which means that analogies work, sort of by construction, because our vector space wanted to make meaning components linear. So this is then showing a gender display. This is showing one between companies and their CEOs. Kind of cool. And you can also do more syntactic facts. So this is showing positive, comparative, and superlative of adjectives. Yeah, so Tomasz Mikolov came up with this idea of doing these analogy tasks. And so he built a data set with a lot of analogies in it. It's sort of it's a bit of a weirdo data set because it sort of tests a few random different things, which may have been things that his system worked well on. But, you know, it tests countries and capitals, you know, cities and states, countries and currencies. So there are a bunch of semantic things it tests, and then there are some syntactic things it tests, so bad, worst, fast, fastest for superlatives. But, you know, even some of the ones I was showing before, you know, there's no Obama is to Clinton kind of ones that are actually in this evaluation set. Here's a big table of results that comes from our glove paper. So not surprisingly, the glove paper performed best in this evaluation because it was our paper. But I mean, perhaps, you know, perhaps the things to start to notice is, yeah, if you just do a plain SVD on counts, you know, that works abominably badly for these analogy tasks. But, you know, kind of as Doug Rohde showed, if you start then doing manipulations of the count matrix before you do an SVD, you can actually start to produce an SVD-based system that actually performs quite well on these tasks, you know, not badly against other things. Other things that you will discover, right, at the top there are 100-dimensional ones, and at the bottom there are some 1,000-dimensional ones and other 300-dimensional ones. At least when you're training on a big amount of text, bigger dimensionality definitely works better, and I'll come back to that in a minute. The amount of text makes a difference as well, right? So we're going up from sort of 1 to 1.5 billion words at the beginning to these ones down here are being trained over 42 billion words of text, and perhaps unsurprisingly, the 42 billion word of text ones work better. So it's big data. Here are a couple more stats from this paper. So this is a graph of dimensionality and what the performance is. So for the 3 lines, the green one's semantic, the blue one's the syntactic analogies, and the sort of red's the overall score. So sort of what you see is up to dimensionality 300, things are clearly increasing quite a bit, and then it gets fairly flat, which is precisely why you find a lot of word vectors that are of dimensionality 300. This one's showing what window size. So this is sort of what we talked about, symmetric on both sides window size. And as it goes from 2, 4, 6, 8, 10. And sort of what you see is if you use a very small window like 2, that actually works, that the syntactic prediction is stronger because a lot of syntactic effects are very local, whereas as you go out, the semantic prediction gets better and better. Actually, the syntactic gets a bit better as well, but it's especially the semantic that gains. The right graph shows that if you only use context on one side, your numbers aren't as good. Okay, so I sort of just wanted to sort of sneak in a little cameos of a couple of recent bits of work, sort of as to what things people are doing with word vectors. So this one was actually by 2 Stanford people. Now this would be the best story if I could say that this was a final project in this class last year, but unfortunately that's not true. This paper has nothing to do with this class. But anyway, Yuan actually had some sort of clever and very mathy ideas where they were using matrix perturbation theory and sort of showing how dimensionality in word vectors actually sort of feeds into the bias variance trade-off, if you've seen that in other parts of machine learning. And I'm not even going to attempt to explain their paper, but here it is. But they did really well with this paper. They got an oral talk at NeurIPS from it. But there's sort of an interesting result of what you see with these word vectors, which is in a way kind of surprising. So this is showing doing word vector dimensions from 0 up to 10,000. So we're going way higher than we talked about before. And so what you discover, which people have known for ages, is that there's sort of a little blip that's somewhere around 200 or 300, which seems to optimize performance. So use those sizes. But the thing that they were sort of doing a lot of their theory about, and it's kind of surprising, is, well, surely if you have a humongous number, like if you're using 10,000 dimensional vectors, you know, you're trying to estimate another 2 orders of magnitude more numbers for every word. Surely things should just fall apart because you've got hopelessly many parameters relative to the amount of training data that you're trying to estimate these numbers from. And so the interesting result that they show is that things don't fall apart and that you can essentially go out to these huge dimensionalities and the performance stays flat, and that they've got a lot of theory sort of for predicting why that's actually going to end up to being the case. Yeah, so for training these models iteratively, this is orange is showing glove training. You know, they keep on getting better for a while, so, you know, just go out, go sleep, see in the morning how it's doing, right? So that if you're running it for 24 hours, your numbers are better than if you only ran it for 6 hours. And that's true for a lot of deep learning models, sorry. So this is the key reason why you don't want to start your assignment the night before it's due, because even if you program it perfectly, you might just not have enough time for it to run so that you produce good numbers at the end of it. Okay. Yeah, so a couple more things on that. Yeah, so what are we showing here? So these are, again, semantic, syntactic, and overall numbers. So there are sort of two things that are sort of being mixed together here. One is if we just look at the overall numbers, they're highest over here, which is this 42 billion Common Crawl web pages corpus. That gives us the highest overall number. But there's sort of something else that's interesting in this graph, which is that using Wikipedia works freakily well, so that you actually find that 1.6 billion tokens of Wikipedia works better than 4.3 billion tokens of Newswire, newspaper article data. And so I think that sort of actually makes sense, which is, well, you know, the job of encyclopedias is to sort of explain concepts and how they relate to each other, right? So that encyclopedias are just much more expository texts that show all the connections between things, whereas newspapers in general aren't trying to exposit how things fit together. They're just telling you about, you know, who got shot dead last night or something like that, right? So, so there's this sort of interesting fact that this Wikipedia data kind of really is differentially useful for making word vectors. And, you know, in fact, you know, when we did very well with our glove word vectors and lots of people use those, you know, I think actually one of the reasons why they work so well is that the original word-to-vec vectors that Google distributes are built only on Google News data, where ours sort of have this Wikipedia data inside them. Okay. Rushing ahead, yeah, so there's all of the work on analogy, but the other more basic evaluation is this one of capturing similarity judgments. And I haven't said much about this, but you know, there's this sort of large sub-literature in the psychology community where people have wanted to model humans' judgments of similarity. So like a good psych person, what you do is you find your classroom of Psych 1 undergrads and you show them pairs of words and say, rate these things for similarity on a scale of 1 to 10. And lots of that data has been collected and you work out the mean over human beings and they give numbers like this of tiger and cat 7.35, tiger similar to tiger 10, book and paper, plane and car, stock and phone, stock and CD, and you get numbers. So then what we're doing is wanting to say, well, let's use distance in the space to map directly onto these similarity judgments and how well does it map. And so that sort of similarity judging has also then been used for evaluating these systems. So again, here are a lot of models. This is again from our glove paper. But so there are these various similarity data sets. So one of the best known ones that I had on the slide before is this WordSim 353. It has 353 different ones in it, and so you're sort of then modeling a correlation between your judgments of similarity and the ones that came from the human beings. Okay, two more things I want to say. Yeah, so we had that problem right at the beginning of Clinton and how that could be various people. And that's perhaps in some sense the simplest case of words being ambiguous when you have names which have reference to different people. But it's not only true of names. So by and large, words in human languages are ambiguous and have lots of meanings. That's especially true of common words. They always have lots of meaning. It's especially true of words that have existed for a long time. It's not true of new, very technical words. You know, carcinoma, I think that only has one meaning. But, you know, if you think of any relatively common word and start scratching your head for a moment, you'll find it has lots of meanings. Maybe this isn't even such a common word, but my random word I've got here is pike. Pike has lots of meanings. It has meanings like a fish. It's a kind of fish, yeah. So there's a fish that's a pike. What else is a pike? A large spear. Yes, so a large spear is a pike. Other kinds of pikes. Gymnastics move or a diving move. It's a road. Yeah. So there are lots of meanings. There are other meanings. In Australian English, pike is also used as a verb to mean to pull out of doing something. Like, we were all going to go out to a nightclub later, but Joe piked. I don't think that usage is common in this country, but you can try it out. Right, but lots of meanings. And, you know, this isn't only true of the word pike, right? Pick any other simple word, right? You can pick a word like shell or field or house or make. You know, they have lots of meanings when it comes down to it. So, you know, but so how can this work if we just have one meaning for words? And that's an interesting question. And it was something that we were actually interested in early on. So even before the Word2Vec paper came out, back in 2012, we were playing around with neural word vectors, and we thought, boy, this is so broken, having only one sense for a word. Why don't we come up with a model that has multiple senses for a word? And so we did that, and we did it in a pretty crude way, I guess. The way we did it is say, well, for each common word, let's cluster all the contexts in which it occurs, and then we'll see if there seem to be multiple clear clusters by some criterion for that word. And if so, we'll just sort of split the word into pseudo words. So if it seems like that there are 5 clusters for the word, the example I meant to use here is jaguar, 5 clusters for the word jaguar, we'll just call them jaguar 1, jaguar 2, jaguar 3, 4, 5. So we'll just literally change the word in our corpus according to its cluster number. And then we run our word vectoring algorithm. And so we get a representation for each of those senses of the word. And basically that works, right? So up the top is jaguar 1 next to luxury and convertible. Here is, I guess, there's a very old version of Mac OS called Jaguar. Anyone remember that one? Right, so Jaguar is right next to software and Microsoft up there, so that's hopeful. Here's the Jaguar that's right next to the Hunter. And I'm a bit confused on this one. This Jaguar is near Solo Musical Keyboard and String. Is there a brand of keyboard called Jaguar? I'm not quite sure about that one. But anyway, it sort of basically works. But that was sort of crude, and it's also perhaps problematic because a lot of time the divisions between senses aren't very clear, right? A lot of senses are actually related to each other and overlapping because how senses normally arrive is that people stretch the meanings of words. It's not that they just sort of randomly wake up the next morning and say, I know, carpet, I could also refer to that as stone and give a new sense to the word stone, right? You sort of take something that you know about, like a web, and you extend it metaphorically to other uses of webbing. So here's a perhaps more interesting thing, and so this is the other Sanjeev Arora paper that I was going to mention. So that what happens if you don't have more than one sense for each word? Well, effectively what you get is that the word vector that you learn is what's referred to by physicists and fancy people as a superposition of the word vectors of the different senses, where superposition just means a weighted average. So that effectively my meaning of pike is sort of a weighted average of the vectors for the different senses of pike, and the components are just weighted by their frequency. So that part maybe is perhaps not too surprising, but the part that's really surprising is, well, if we're just averaging these word vectors, you'd think you couldn't get anything out of the average, right? Like if I tell you I'm thinking of 2 numbers and their weighted sum is 54, what are my 2 numbers, right? You're sort of really short of information to be able to answer my question. But well, for these word vectors, we have these high-dimensional spaces, and even though there are a lot of words, the space is so vast with all its dimensions that actual words or senses are very sparse in that space. And so it turns out that there's this whole literature on sparse coding, compressed sensing, some of which is actually done by people in the stats department here, which shows that in these cases where you have these sort of sparse codes in these high-dimensional spaces, you can actually commonly reconstruct out the components of a superposition, even though all you've done is sort of done this weighted average. And so this paper looks at how you can do this. And so they have these underlying meaning components, and they sort of separate it out. So tie has one meaning component that's in this space of trousers, blouse, waistcoat. That makes sense. Another one in this meaning component of season teams winning league makes sense. Scoreline, goalless, equalizer, clinching, scoreless. This one seems to overlap with this one a bit. But here, tie, this is sort of cable ties and wire ties and things like that. So they're actually able to pull out the different sense meanings from out of the meaning of the word. So that is a kind of a cool thing. I just want to say one more thing. Okay. All the evaluation so far was intrinsic. You also might want to do extrinsic evaluation. Why word vectors excited people in NLP so much is it turned out that having this meaning, having this representation of meaning just turned out to be very useful and sort of improve all of your tasks after that. And so this is doing named entity recognition, which is labeling persons and locations and organizations. But it's typical of many tasks of what people found was if you started with a model without sort of word representations and you throw in your word vectors regardless of whether they're word-to-vec or glove ones, just kind of your numbers go up a couple of % or more. And so the word vectors were just sort of this useful source that you could throw into any NLP system that you built and your numbers went up, so that they were just a very effective technology which actually did work in basically any extrinsic task you tried it on. Okay, thanks a lot.